The last problem we're going to do is this one. A rope is attached to a weight that goes up through a pulley 30 feet above the weight and back down to a worker. The worker holds the rope at the same height as the connection point between the weight and the rope. Suppose the worker stands directly next to the weight and walks away at a rate of 2 feet per second. How fast is the weight rising when the man has walked 10 feet and 40 feet away from the weight? Let's draw a rough sketch of what's happening here. We have a weight, which we'll draw as a big gray weight, and it's attached to a rope that goes straight up to a pulley. So just pretend this rope goes around the pulley and then back down to a guy. So some worker, I don't know if it's a man or a woman, but I think it says a man, but I can't remember. So some guy's right there holding the rope. And this person is going to walk away in this direction. Now, if you think about it, when that person walks to here, and he's holding the rope, what's going to happen is that because he walked away, the weight is going to be lifted as long as he's strong enough to lift the weight, right? As long as this worker is strong enough. So that's what's happening. It's the relationship between the distance walked and how this weight is being lifted. That's the thing to think about. This one is going to be a little bit tricky because we have to take into account a couple of different aspects at the same time. The first is this overall triangle that we're making from the base of the weight up to the pulley, down to the person, and then back. This is why we wanted to have the connections at the weight and the person to be at the same height. So we have this right triangle that does this. So the side here, let's just pretend it just stays the same. So this right triangle here, from where the weight once attached to where the hand of the person is and to the pulley, we can call that A, B, and C. But this ABC is not the entire story. So the ABC we can see forms a right triangle. But there's also this other aspect that if I'm pretending my A is constant, and in this case I'm going to, then there's going to be this other letter D, which just follows the rope. So the rope is part way up here, right? As we walk away, we lift the weight. So the D is going to be the length of the rope from the weight up to the pulley. So A here, I'm always going to pretend is 30. That's how I'm going to find, given how far this person has walked, that's how I'm going to find the hypotenuse of that triangle, which is the length of the rope from the pulley to this man's hand. And the other thing I'm going to utilize is the fact that the length from the guy's hand to the pulley and back down has to be 60, because if you recall, the pulley was 30 feet in the air from where it attaches to the weight. So it went up 30 and back down 30. So the rope had to be 30 plus 30, which is 60. And that means this length, D plus C, always has to be 60. So C plus D equals 60. And then we can use the Pythagorean theorem with 30, B, and C. So we're going to use two things at the same time. We have two equations here. And just for the record, what our question was asking is, as the B, the length from the weight to the man, the original spot of the weight to the man increased, how does it look like the weight is being lifted? So what's the distance between the pulley and the weight? How is it going up? The A here, I had always set equal to 30 because that's the original where the weight attaches up to the pulley. And then we can do two things at the same time. We're going to figure out the relationship between a change in B and a change in C. And that's going to cause a relationship between the change in C and change in D. Or I should say, then we'll use that to find the change in D via this relationship. So I'm going to take a derivative of both of these and kind of go through this equation first and then this equation. Now you could, at this stage, if you were clever, you could combine this into one big equation by solving for C and then substituting in. But I think it's just as easy to go through two equations each time. So let's take a derivative of the first equation with respect to time. Well, 30 squared is constant, so that becomes 0. B squared, derivative of that is 2b multiplied times the derivative of b with respect to time. Derivative of c is 2c multiplied times the derivative of c with respect to time. The bottom equation is really nice. 1 is the derivative of c, so 1 multiplied times dc over dt is equal to, minus 1 times derivative of d, well, that's going to be confusing, over dt. Maybe I'll use a different letter. Let's use derivative of x. Equals derivative of 60 is 0. So what's this mean? This means the change in the length of rope from the man's hand to the pulley is the same as the change in the length of rope from the pulley down to the weight. I hope that makes sense. If this length were to increase by 2, then this length, it goes up by 2. Again, we're calling this x here. All right. So there we go. Call that x to avoid a DD scenario. Just to go back to the original problem. Remember, this person is walking away at a rate of 2 feet per second. And we want to find how fast the weight is rising when this person is 10 feet away and when this person is 40 feet away from his original starting point. Let's start by calculating what's going to happen when this person is 10 feet away. Remember, the 10 feet away was the base, so that's the B here in this equation. I'm going to need a B and the C, so let's go ahead and figure out when the person is 10 feet away, how much rope is between the person's hand and the pulley. If I solve this equation, you get that the hypotenuse is the square root of 1,000, which does not turn out to be real nice. Hopefully that's not too fast. Just calculate this, you get 1,000. 1,000 is equal to C squared. So take the square root, you get square root of 1,000. So C is square root of 1,000 when the man is 10 feet away from his original starting position. Now we can plug in all of this stuff into our function. When the man is 10 feet away, the rope length is the square root of 1,000. And the person is walking away at a rate of 2 feet per second. That's the dB, because you're walking away at the base in that direction of 2 feet per second. If I want to find out how fast the rope is increasing, the length of rope is increasing, I solve this. 2 times 10 times 2 divided by 2 times the square root of 1,000. I got approximately 0.6325. That's dC dt. That's also dx dt, because we know dC dt is the same thing as dx dt. So what that means is that the rope is increasing, or the weight is increasing. Let me say it that way. The weight is raising at a rate of 0.6325. That would be feet per second. So that's the rate at which the weight is rising. Let's go ahead and do the same thing if this person who's holding the rope is 40 feet away. If the person who's holding the rope is 40 feet away, then what happens is all these numbers change. 30 squared plus 40 squared is 2,500. So the length of rope is the square root of 2,500. That's actually a nice number, that's 50. So C is equal to 50 in that scenario. We go back to our equation that relates how far away the person holding the rope is from the length of the rope from the person's hand to the pulley and the rates of changes. If this problem says the person is 40 feet away from the starting position, Remember that they're walking away at 2 feet per second. Now we know the length of the rope is 50. I can solve that. 2 times 40 times 2 is 160, divided by 2 times 50. So that's just like dividing by 100. You end up with 1.6. That's the way how much rope is increasing from the pulley to the guy's hand, which is also the rate at which the weight is being raised. So the weight is being raised at a rate of 1.6 feet per second. That's how that problem is done. Again, I think it's easier just to see that because the sum of C and X is 60, that they have the same rates of change, and then use this equation here. And that should make sense. The rate at which this rope, this length here from the person's hand to the pulley is increasing is the same rate as how this weight is being lifted. Because each additional unit, each additional foot of rope from the hand to the pulley is 1 foot that we've raised this weight. So there you go. That's how we deal with related rates in this section.